Hello, and welcome to Astronomy 100. In this segment, what I'd like to do is spend a moment to summarize some of the topics that we've been describing for the last few segments. If you recall, we're going through the section that describes what we call remote measurements, the ability to learn about objects that are too far away for us to reach and do our traditional means of measuring things. So we're going to go through the topics from the beginning to the end, just sort of pulling them all together into a summary, sort of a review. So let's start with the first one. If you recall from when we started this, the idea is that light is the carrier of information. Information about the object making the light will carry information, of course, through the method of light and how it travels, and that light that comes from the object will come to us, and we'll learn about the object making the light. So what we started with was the idea that light has a speed. It does not travel infinitely fast. It has a speed, and so when it goes from one place to another, it travels at 186,282 miles per second. The speed of light is constant. It's a value that never changes, and all forms of light travel at the same speed. Then what we did is we talked about how because light has a speed that it travels at, it requires time for light to go from one place to another. And so when we look at objects that are very far away, we are seeing these objects that are, of course, far enough away where the light has taken many, many years in most cases for that light to reach us. So essentially we're looking back in time. And the examples that we saw is that when we look at just some of the basic stars in the sky, we are seeing these stars the way that they looked hundreds of years ago, sometimes thousands of years ago. So it simply requires time for light to travel these immense distances. And this allowed us to create the unit of distance called the light year. And remember that 1 light year is the distance that a beam of light will travel in a year's worth of time. What we then did is we talked about how light has a way in which it travels from one place to another. In other words, when light leaves a source and travels across space and reaches its destination, there are essentially two ways in which light can travel. We can describe light as traveling as a wave of energy, and the peaks that you see here are traveling at the speed of light from one place to another. Or we can think of light as a series of particles of energy. And of course, these particles are called photons. And these photons travel at the speed of light. And the beam of light is just essentially a combination of all these photons coming from the source. Remember that both of these descriptions are correct. Neither one is better than the other, or neither one is more correct than the other. Light can be thought of as a wave, or light can be thought of as a particle when it travels from one place to the other. What we then did is we talked about the nature of waves. Remember that waves have measurable properties, and those properties were the speed of the wave, the wavelength of the wave, where the wavelength is the distance from one peak to the next peak, and then we talked about the frequency of the wave. And the very important idea of how color and wavelength relate to each other. So if you recall, when we perceive color, what we are actually seeing is light of different wavelengths. And when it comes to humans, we have the ability to see light that has a wavelength that is shorter than 7,000 angstroms, but longer than 4,000 angstroms. So essentially anything that is longer than 4,000 or less than 7,000 is going to be the colors that we perceive. 7,000 angstroms corresponds deep into the red, and 4,000 angstroms corresponds to violet. And so wavelength is our perception of how the brain treats wavelength is how we perceive color. So the color that we see coming from something is essentially the wavelength of the light that is being emitted by the object. What we then did is we described light as a particle, and remember that we invoked the term photon. When a source of light is shining, of course, the light across the room, we can think of it as a series of photons. Each of these photons travels at the speed of light, and if you recall, we use the abbreviation of the letter C to symbolize the speed of light. And essentially, photons are the carriers of energy, and each of these photons has a certain amount of energy that's associated with it. When we see red photons, we are seeing photons of lower energy compared to photons that are violet. So a violet photon carries more energy and a red photon carries less energy. The energy of the photon is inversely related to the wavelength of the light. If light has a very long wavelength, then therefore the energy of the photon is low. And if light has a very short wavelength, then the energy of the photon is high. So it's an inverse relationship. What we then did is we wrapped everything together into one concept called the electromagnetic spectrum. And if you recall, this is the range of all possible wavelengths that our universe is capable of producing. We have light that is essentially all the same thing, but can have different wavelengths and of course different frequencies. And so when we consider light that is of the shortest wavelength possible, this would be what we call gamma ray light. And then when we talk about light with the longest wavelength possible, this is what we would call radio light. And so everything in between is simply light that has a different wavelength, either in this case getting longer than gamma ray as we go to radio, or if we go in this direction, it is wavelength getting shorter as we get to the realm of gamma ray. And visible light happens to be right here. There's a certain range of wavelengths that we are capable of seeing. If you recall, that's 7,000 angstroms down to 4,000 angstroms. And so what we are actually perceiving with our eye is just a tiny little part of the electromagnetic spectrum. There's an enormous amount of light that the universe produces that we're incapable of seeing because the human eye cannot see any wavelength shorter than violet or any wavelength that's longer than red. So even though we like to think that what we see is what there is, in reality, we are only seeing a small portion of the amount of light that the universe produces. There are many, many sources in our universe that will produce light that our eyes are just incapable of registering. Now, when we wrap in the idea of the energy per photon, of course, if we go back to the electromagnetic spectrum, what you can see is that when we talk about the energy per photon, that means that, of course, gamma ray photons are the highest energy, radio photons are the lowest energy, and of course everything in between. So when we consider the colors that we see with our eyes, we are essentially seeing photons of different energies. Low energy photons in the visible are red, and high energy photons in the visible are violet. What we then did was start to use some of this information, but we wanted to wrap it into our methods of determining the features and the details of objects that are too far away for us to measure. And one of the things that is very important for us to be able to learn about the objects of our universe is to measure the temperature of the object. The temperature of an object tells us an enormous amount of information. And so the key thing to remember is the definition of temperature. And if you recall from the segment, we talked about how temperature is a measure of the average velocity of the atoms or molecules. So when you are measuring the temperature of something, what you are actually measuring is the movement of the atoms or molecules. And the example we used is if you look at the atoms that are inside of this box, you can see that they're all moving, but what will happen, of course, is that they're moving at different velocities. And as they move at different velocities, they will, of course, bang into each other and bang into the box. But when we increase the temperature, you'll notice they move faster. And when we decrease the temperature, you'll notice that they move slower. So temperature is a measure of the average velocity of atoms or molecules. And then, of course, the idea that everything in the universe has to have a temperature associated with it as well. Now, using this concept of temperature, what we then did was we invoked what was called Stefan's law. And this was a very, very critical step because what Stefan's law will tell us is that the temperature of an object will determine the energy of the photons that are being given off by that object. And the example we used was that when we take a piece of metal and we heat up that metal to higher temperatures, you'll notice that the color coming from the metal, the colored light, will change as well. And so when we first see something get very hot, it'll start off as red hot, but then the hotter it gets, it turns white hot, and then the hotter still it gets will turn blue hot. So the reason why this is changing is because color is a function of the photon energy. So red photons carry the least amount of energy and blue photons carry the most amount of energy. And if the temperature is becoming higher, if T is getting bigger, then of course the energy of the photon also has to get bigger. Now, this one key piece of information was important because it allows us to determine the temperature of an object just simply by the light that it produces. And the way that we actually turn that into a number is we use the concept of Wien's law. And Wien's law simply says that the features of a black body curve are going to change based on the temperature of the body. And if the temperature decreases, the black body curve shifts one way. If the temperature increases, the black body curve shifts the other way. And by determining where this peak is, we can actually figure out what the temperature is of the object producing the light. And ultimately what this leads to is the ability to measure the temperature of something without having to physically touch it. And the example we used at that time was to determine the temperature of the sun. We simply figure out the energy of the sun, pass it through a prism, take the light, pass it through a prism, produce a black body curve, determine the peak, figure out what wavelength that is, plug it into the formula, and this now tells us the temperature of the sun. And this is, of course, why stars are of different colors. Stars that are very, very hot are going to look blue, and stars that are relatively cool are going to look red. Just like that piece of metal starts off red and then of course works its way to become blue if that piece of metal gets hotter. So stars of different colors are stars of different temperatures. Now the last little bit of this was, how do we figure out what something is physically made out of? And if you recall, when we take the light from any star, the sun in this case, and we pass the light through a prism, what we end up getting is all of these mysterious dark lines that we called spectral lines. And we found that it was Bunsen and Kirchhoff in the middle part of the 19th century that discovered that each element on the periodic table produces a unique pattern of lines. And so if you can identify the pattern and the element that creates that pattern, then what we can do is we can look at all of the lines coming from a star, or the sun in this case, and we can actually tell what the elements are that the sun is made out of. So spectral lines help us understand the chemical nature of an object producing light, because the spectral lines will tell us what the object is made out of based on the lines that it produces. And then the very last bit of this was we went through the physics of how these lines are produced. If you recall, Kirchhoff was able to tell us that in nature we end up with 3 types of spectra. You can have a continuous spectrum, you can have an absorption line spectrum, and you can have an emission line spectrum. Even though the pattern is the same, the spectrum itself has different features. Colorful background with dark lines, dark background with colorful lines. And what we did is we talked about how all of this is caused by atoms, and how the atom with its internal components, the electrons, the protons, the neutrons, and the rules that govern how the atoms behave will tell us how these lines occur. Ultimately, it boils down to how every element on the periodic table has a different set of protons in its nucleus. That's the atomic number. And the number of protons determine the orbit levels for the electron. And if the electron has a different configuration of orbital levels, then as the electron jumps from one level to the next, it produces a different type of line. And if each element has a unique pattern of lines that it produces, it's because each element has a unique set of orbital levels that the electron is capable of jumping to and from. So ultimately, the electrons going from one level to the next is going to produce either an absorption line spectrum, an emission line spectrum, or in some cases a continuous spectrum. And the pattern that we see is related to how the electron's jumping from one level to the next. Now, the final piece of this was when we actually put this into practice, when we do this for real, what we end up doing is we create graphs that represent these patterns. So what we saw was that in this case of an absorption line spectrum, you get the very colorful background with the dark lines. But what we really want is to make a graph of this picture. And so all of these dark lines are represented by these dips that you see on the graph. You have a very colorful background, and then you have certain colors missing. And each of these colors that are missing, of course, have a certain wavelength. So what the graph tells us is the actual colors that are missing and how dark each of the lines are. And that piece of information can tell us many things about the star that is producing the pattern. And of course, we saw some examples. Here is what a real absorption line spectrum looks like. And this one over here on the right is what an emission line spectrum looks like. You have a dark background and certain colors that are present versus a bright background with certain colors missing. So all of this helps us understand what the chemical composition is of the star or the object that is producing the light. So what you can see is that throughout this entire series of segments, we now have the ability to determine the physical properties of the objects we want to study. When we want to know what something is made out of, the light will tell us that information. When we want to know the temperature of an object, the light will tell us that information. Because ultimately, light is the carrier of information. So I hope this helped you understand by pulling this all together and seeing how all of this works together. We're just about out of time, so I hope you'll join me next time.